The Smith chart can also be used for calculating or plotting impedance. Let's suppose, for instance, we want to plot a load that has a real and an imaginary impedance. The first thing that we do is we normalize all of our values by Z0. So we take our value right here and we're going to plot the real part divided by Z0 and the imaginary part divided by Z0. The places that we plot the real part I'm going to show you in green. There are several circles here. This one right here, for instance. See that circle? That's a real circle. This circle has a real part of 1. Here's another real circle. This real circle has a magnitude of 0.5. Here's another real circle. That one has a magnitude of 2. So I hope you can see several real circles here on this Smith chart. We read their magnitudes right off of this axis here. The way we're going to plot the imaginary parts, I'm going to show you in blue. These are also circles, but you can't see their centers on the Smith chart. Here's the imaginary that has a magnitude of 1. And here's the imaginary that has a magnitude of 0.5. Say this is a circle. It's actually part of a circle with the center off the Smith chart. And here's the imaginary part with a magnitude of 2. The imaginary part of 0 is right here along this line. And then when we go below that center line, the values are going to be negative. This is going to be negative 0.5, negative 1, and negative 2. You can remember that they are negative because they tell you that this is the capacitive side and they tell you that this is the inductive side. So let's suppose, for instance, that I have a load impedance that is 50 plus J50 ohms. And let's suppose that my characteristic impedance is 50 ohms. So when I normalize it, I want to plot 1 plus J1. So let's first go find the real part of 1. That's this circle right here. And the imaginary part of 1, positive 1, that's this circle right here. At the intersection of these two circles right here, this is Z load equals 1 plus J1. Now let's see what would happen if this had been 50 minus J50 ohms. I would still have normalized by my 50 ohm characteristic impedance, and I would have gotten 1 minus J1. So the real circle would be the same. The imaginary part would be this line right here, which is negative 1. So this point right there is ZL equals 1 minus J1. Now let me show you how to get the reflection coefficient from these two load impedances. What we're going to do is put a dot right here at the center, take my straight edge or my piece of paper, and draw a line straight out to the outside like this. That's going to give me the angle of the reflection coefficient if I look at the line that I previously had highlighted in yellow. That means that the angle is 65 degrees, about 65 degrees. To find the magnitude of the reflection coefficient, take your straight edge, your piece of paper, and mark this distance. Bring it down here to the reflection coefficient axis. Start at the center and put that distance right there. Looks like it's about 0.5. So the magnitude of the reflection coefficient is 0.5 and its phase is about 65 degrees. Now what about our other one? Let's look at this one down here at the bottom. We want to find the reflection coefficient by drawing a line from the center through my point out here to the outside axis. I can see I didn't get these quite lined up because my angles would have been conjugates of each other. So I'm at about minus 62 degrees right there. That's the phase of the reflection coefficient. My magnitude is going to be the same. Again, mark it right here onto your piece of paper, bring it down, start at the center, put another spot right there. The reflection coefficient magnitude is 0.5.